Hello. Can you hear me? Yes. So hi, I'm Ryan. I'm going to just give you a little introduction to Node and what its goals are and what it does. So just really briefly, Node's a set of bindings for Google's V8 JavaScript virtual machine. And it allows one to script programs that do I/O in JavaScript, which is something that JavaScript previously hadn't really done so much of. JavaScript was restricted to the browser and didn't really have any notion of doing I/O other than manipulating the DOM. And well, it does I/O in a very particular way, and that's the only reason it's exciting. And I'm very focused on making it fast. So first, just a ridiculous benchmark. So let's take a web server and put 100 clients on it and have them hit the web server as hard as it can and give you a 1 megabyte response each time. Of these 4 web servers, Node actually performs the best, which, if you're familiar with Nginx, it's written in C. It's completely written in C. It's this totally optimized, event-looped C web server. And Node can actually push out data faster than that. So here's the code for that benchmark. I'm not actually writing a string to the server. Well, let me explain this first. So on line 1 and 2, we require modules. This is using the CommonJS module system. So there's an HTTP module and there's a buffer module. And this buffer is something to allocate raw memory, something that JavaScript isn't particularly good at it. And then in lines 4 through 6, we fill the buffer. We allocate a buffer with a megabyte of memory, and we fill it with a bunch of bytes. And then in lines 8 through 11, we create a web server, and we give it a callback which is issued each time a request comes into the web server. And what the callback does is it writes out 200 OK HTTP head, and then writes out the buffer to it. And then the last line makes it listen on port 8000 of localhost. OK, so some stupid code, but it's really fast, like really, really fast, right? I want you to take this with some grain of salt. The Nginx process was using 4 megabytes of memory, and Node was using 60 megabytes of memory. And these are pretty, this is a pretty specialized program where you're writing out just one chunk of memory all the time. Nginx was serving a 1 megabyte file, so it was probably doing some file system polling. There was probably a lot more going on there. But nevertheless, it's nice to see that your web server could possibly be serving static files from memory at a speed that is equivalent to an optimized C web server. OK, so it's kind of fast. Let me just do a little bit of philosophy around this. We're doing I/O completely wrong. Like, we really got screwed up at some stage. And we could be doing it differently, and things could be much easier than they are. And this program is my attempt to demonstrate how we could be doing I/O more easily. A lot of applications, web applications in particular, but applications in general, have a line of code like this where you query something. You access a database that might be on the same computer, or it might be in Los Angeles, but you do some I/O, but you abstract it in the form of a function where it goes out, does that I/O, And then, you know, Los Angeles responds, and then you return from that function as a result. And the question is, what does your software do while this function is going on? And in many cases, like Rails, you do nothing at all. You make a database query, and your process shuts down. And that's really not acceptable in well, really anywhere. But in very few circumstances is it acceptable to have a process sitting there that has clients waiting to be served, but is doing nothing at all. So here's some things I pulled off the internet. To access the L1 or L2 cache, it's really fast. It's a couple of cycles. To access RAM, a couple hundred cycles. But to go out to disk or network, it's millions of cycles. We shouldn't be treating accessing these top three things the same way that we treat these bottom two things. They are fundamentally different, right? I heard an analogy where, like, you know, accessing something in your CPU is like working at a desk and opening the drawer and pulling out a piece of paper. And, you know, maybe getting something from RAM is like walking across the room and like talking to somebody and getting something and coming back to your desk. But going out to disk is like, you know, getting in a plane and flying to Tokyo and grabbing a piece of paper and coming back. You can't sit there and block the process. So just a bit of terminology. We call functions that just access memory, basically, non-blocking functions, and things that go to disk or network, blocking functions, because there's such a big Unterschied. There's such a big difference between these two things. So this blocks, and it's very important to realize that that blocks. But in almost all software, we don't talk about this at all. We have some function, and we call it, but what's it doing? Is it spinning the disk? Is it talking to Los Angeles? We have no idea because it's just some function in some API. And then we sit there and wonder why our programs are slow. We have no idea what's going on in our programs. Obviously, not all software blocks when you make a call to a blocking function. Better software can multitask. You can have multiple threads of execution running, and when you block on one, you switch to another one and continue. But are different threads of execution the best way to do this? If you look at Nginx and Apache, which are two web servers, very popular web servers, here's a benchmark I got off the internet. On the x-axis here, on the horizontal axis, is number of clients at the same time connecting to the web server. And on the vertical axis is requests per second. So bigger is better here, right? You want to respond faster. And right, so Nginx is faster, but I mean not so much faster. It's only 3 times as fast, which really wouldn't be so much of a concern until you look at the memory usage, where you see that Nginx basically stays very stable in terms of memory, while as you add more concurrent clients to Apache, the memory usage just climbs and climbs. So for situations where you have a lot of users sitting on your web server, for example, a chat, maybe they're not doing anything, they're just sitting there idle. Apache can't handle it because it creates a thread for each of these things. Right, so the difference between Apache and Nginx, the real difference is that Apache uses a thread per connection, and Nginx uses an event loop. So context switching between threads isn't free. It slows you down. It's fast. Of course it's fast. Like the Linux scheduler is very, very fast. But it's not free. And if you have OS threads, they take up space, right? They are 2 megabytes or a megabyte. They are not free either to just create thousands and thousands of them. So for really massive concurrency, it's pretty much clear to everybody that you can't use an OS thread for each connection. So the situation changes very much if you talk about a green thread system or coroutines or one of these things. You can get what I said before only applied to OS threads. But even if you talk about green threads, there's still machinery involved there. Maybe the machinery is very good, but there's machinery involved to make it seem like when you call that function to query the database, that your program is halted. It's not halted. Well, maybe it's halted if you're Rails or something. Maybe you just stop and don't do anything, which is bad. But if it's not halted, your program's doing other things. It has to create this illusion of just halting there. And that abstraction costs. Right. So if you have blocking code like this, where you abstract I/O into a function call that returns the result of the I/O, you're either blocking the entire process, which is usually unacceptable, or somehow you have multiple execution stacks involved. You have some form of threading. Maybe it's green threading and the execution stacks are very cheap, but there's something. There's something more than nothing. But if you had a line of code like this, where you made the query and then you gave a callback to that function, the interpreter can run right through that, right? It can make that query, whatever, write it to the kernel send buffer, and then keep going and start doing other things. It doesn't need to wait for Los Angeles to respond. There's very little machinery here. All it is holding a pointer to that callback and then telling the kernel to inform us when that response comes back from it. So this is how I/O should be done. Right, if it's so great, why isn't everybody doing it? Well, there's very good reasons why you wouldn't be doing this. There's a lot of reasons, cultural and infrastructural. We have this cultural bias towards writing blocking programs. Our first I/O program that we're given, it says enter your name, and then you block, and you wait for the person to enter their name, and then you print out their name. It's blocking I/O. And from the beginning, we're taught to think of I/O this way. It's fine in this case when your program does nothing except wait for the one user. But if you have 1,000 users all waiting to enter their name like this idea doesn't work. Code like this, where you give a callback, which is what you would need to have a server that printed out your name to you, where you telnet into it and it did this exact thing, same thing. It just gets rejected outright. People say, no, that is way too complicated. We can't do that. It's spaghetti code. It's much too hard. Well, maybe not everybody. Really, the bigger problem is the missing infrastructure. If you're in a single thread and you're doing this event loop thing where you say, okay, kernel, tell me when that socket responds, and I'm going to do all this other stuff, you're really in a single thread. You absolutely cannot block, because if you block, everything else gets stopped. In a threaded environment, you can block on one and other things can keep going. But here you have to be very, very careful not to block on any I/O. And the libraries that we use are very often blocking libraries, and there's no way around that. So some examples. So accessing the disk. You can't do it. You cannot do it, right? You can't access the disk without blocking. Supposedly there's like some POSIX async specification out there, but it's just not available on machines. Man pages don't tell you if a certain call is going to access the disk or not. In C, you don't have the language features that make writing with callbacks nice. You don't have closures and you don't have anonymous functions. And so doing this sort of evented style programming becomes very tiresome. And database libraries, which are usually very important to write web applications. In particular, libmysql client, like a very popular library, doesn't have a non-blocking interface. So are you willing to rewrite libmysql client, or are you going to use threads? And almost everybody says, we'll just use threads. You know, it's not that much worse. And a really big problem is asynchronous DNS resolution. It's not there. It's unavailable. You have to block on DNS resolution. These days, people have been writing libraries to get around this. But if you don't have these things in place, and you just want to sit down and write a program, and you just can't get around these roadblocks, right? Not unless you're willing to rewrite libmysql client. In other cases, in Ruby and Python and Perl, there's this event machine twisted and any event, respectively. And they provide very easy platforms to write non-blocking event loop code. It's pretty easy to take them and write very fast, efficient servers. They're great libraries. But the everyday user coming to this is kind of confused about how they take Twisted or Event Machine and combine it with all the other Ruby infrastructure or Python infrastructure. So it turns out that it still requires an expert to write an Event Machine server, if only because the person who writes it needs to know what an event loop is, what a non-blocking function call is. Maybe this is trivial knowledge, but it's something, right? And so you can't just pick it up and start writing something like this, because as soon as you throw in the default Ruby MySQL client library, it blocks, and now your server sucks. So what's really nice is browser JavaScript. Man, they got it right. They really got it right. It's just amazing. It's designed specifically to be used within an event loop. So it has all these nice language constructions like anonymous functions and closures. But the real beauty is in the programming model of the browser, where you just get these callbacks. Somebody clicks a button, you get a button clicked callback. And only one callback happens at a time. No browser user has ever heard of an event loop or non-blocking I/O. These concepts are not necessary for them to program a website. And it's because they are restricted to this very enclosed environment where they are only given this very certain specific type of I/O. So the culture of JavaScript is really already geared for evented programming. So the Node project, to end my long-winded philosophical section, is to provide this purely evented, non-blocking infrastructure to make these highly concurrent programs that are possible, but the users need to be put in a jail, right? They can't be trusted. You cannot give them blocking functions. They won't know what to do. You can't tell them about event loops or anything like that. You just have to put them in there and let them do their thing, and then they'll hit it with Apache Bench, and they'll say, wow, it's fast. That's great. Cool. I'll make my website on this. Put them in a jail. Don't let them do anything stupid. Okay. So design goals. No function should directly perform I/O. This isn't totally true, but mostly true. So to receive info from a disk or network or another process even, you have to have a callback. So this creates a really kind of nice, people hate callbacks, but once you start using it for a while, it creates this really neat environment where you can see exactly where I/O occurs, right? Sorry, I'm going to deviate from the slides. So if you have some function and you say, call A and return B, in Node, you know that no I/O is being performed here because no function directly performs I/O. It's very clear that when I/O occurs, you go in an indentation level. It makes it very clear where you are accessing something that's slow. You go in. Like, you can visually see where the I/O is happening. Yes?
I would think that that observation applies to I, but not necessarily for O. Why is it that the first thing without the indent level, if it's only output, it doesn't need any feedback, couldn't be doing output?
It could be output. It could be actually like writing to a socket or something like that. That's right. I guess what I mean to say is that you're not receiving any data. Yeah. So in Node, there are lots of queues where you can write data to disk, and you can say, you know, puts to the standard out or something, and it's not some callback thing where you get that, but that's kind of a convenience sort of thing. There's an internal queue that kind of pushes that out. But yeah, you're right. I/O does occur inside functions, but to receive data, you definitely go in an indentation level. So it should be low level. We need to get our hands on web servers and what they're doing. It can't just be a big red button that you push and it starts up a web server, but you can't get into the internals of it. In particular, everything needs to stream. At no point can it just buffer up the entire HTTP response, because that's just not acceptable if the HTTP request was a movie, for example. So there's a lot of streams happening in Node. And I don't want to remove any functionality as much as I can. I don't want to remove functionality that you have at a lower level. So for example, half-closed TCP connections. Almost nobody cares about them. But why remove them? Why remove the ability to cat a file to some network device and have an EOF at the end of it, but have the other side still respond afterwards with a checksum or something? And then we should have built-in support for really important protocols, right? The internet isn't just IP, right? Let's just be honest. You have to have DNS, you have to have HTTP, and yeah, you pretty much have to have TLS, right? Transport layer security. These are infrastructural protocols. It's not Jabber protocol, right? Yeah, I mean, that's cute and people use it, but it's not the foundation of the internet. These three protocols are the foundation of the internet, and everybody needs to speak them. So let's just do it right. Let's sit down and make really nice libraries for this. HTTP is extremely difficult. So is DNS. Let's just sit down and do it in a way that we can use it really well. In particular, I'm a bit of a HTTP nerd, so support all the cool features like chunked encoding and pipeline messages, which is actually really important, right? You can't close the close this TCP connection for every single request and spin it up again, right? For a real web server has to support pipeline messages. And of course, for doing chats and real-time sort of things, you need to be able to make a request to a web server and let it hang while some events accumulate, and then let it respond at a later time without completely screwing up the web server. And so it can do that too. Right, and the API should just be familiar, right? If we're going to have a timeout function for calling this callback in the future, let's call it set timeout. Let's not make up some new API. But if we're talking about something that's something server-side, like TCP connections or something like that, let's just use the Unix names for them. I don't want to make up names. And be platform independent, because it's useful. And be simply licensed. It should be, it is almost 100% MIT BSD. The only exception is OpenSSL, which has its own library, its own license. But everybody uses it, so it's kind of accepted. Few dependencies, static linking, and most importantly, just make it enjoyable, right? Like, I'll package all this stuff up, and everybody can just download it and compile it and use it, and it'll be fun. So here's the architecture. It looks like this. There's V8, which does the JavaScript execution, and there's a thread pool, which I use to do all these like blocking file operations, right? I can't do these file operations, so I have to send it to a thread. And the event loop, which is libev. So basically, this is just a wrapper around select. It's a little bit more than that, but it's pretty basic, right? It's a wrapper around select. But you know, if I'm on Linux, it compiles to epoll, and if I'm on FreeBSD, it compiles to KQ, and if I'm on Macintosh, where everything sucks, it compiles to select. KQ is very buggy in Macintosh. And the thread pool is also extremely simple. It's just a thread pool. And then there's some bindings, which are in C to JavaScript. And then actually, the most of Node is written in JavaScript these days. So the JavaScript layer is just the main thread. You are in one execution stack. But at the C layer, you can use multiple threads. So for example, you wanted to write a gzip library and fork it out to like 5 threads. You can do that and write a little Node module for that. But it has to be in C. Is this a deficiency? No, it's a feature, because threads should only be used by experts. And I don't think people really believe that. And maybe they believe that, but then they say, oh, I'm an expert. No, you write it in C. That's a good boundary. Jail users in a non-blocking environment don't allow I/O trickery, like coroutines. And yeah, there's only one execution stack. So let me just very quickly show you what it looks like when you receive a request. So here is the execution stack. This is the libev event loop call. Pretend it's select, okay? And somebody connects to your web server, and now you get a call. The select returns. You get a callback in some fashion. You are told that the socket number 1 is readable. So you read some data from it. You parse it, and the HTTP request was to index.html. You don't have it in memory, so we actually have to load up this stuff. We have to load it from the hard drive. So what Node does is it sends a request to the thread and says, okay, thread A, thread number 1, please load this index.html and let me know when you're done. The stack unwinds. We're back to the event loop. Okay, so the request is sent to the disk. We sit idle. Millions of clock cycles in the future. We will hear back from this thread, okay? But that is way, way, way in the future. In the meantime, somebody else connects to our server, and this time they're just requesting something simple, something that we have in memory. And so we're sitting at our event loop, and we get a call that says, oh, socket number 2 is writable. Okay, let's parse that request. And we can just respond to it now, because we have that in memory, and we can just send that out. The stack unwinds. We're back to the event loop. The process sits idle. The first request, the person waiting for that website, is still waiting. Mind you, this is very small time scale, so not so long. Eventually, the disk comes back and responds to us. And we get this callback that says, oh, now index.html is loaded into memory. We did that for you. Thank you. Here it is, pointer to it. And now we can respond to the first request. It's just one stack. It's very simple. I really like one stack. If you have coroutines, you have multiple stacks. If you build up at some point and then yield and then you go back to the event loop, and new I/O is occurring, and then you return from that yield, and now you're in a completely new state of the world because all this I/O has occurred. That's too complicated. Why? Like, so we can make like something look blocking? Forget it. Let's just keep it simple. I mean, this is hard enough. Just one stack. Okay, so quickly, a couple of examples. Right, to use it, you download it, you configure, make install. There's no dependencies other than Python. V8 comes with it. So here's an example. We're going to load the sys library, which allows you to output stuff to the console. And in lines 3 through 5, we do a set timeout, just like on the browser. Okay, and we do it for 2,000 milliseconds. And then on line 6, we print hello. So what does this program do? First, it prints hello, and then it prints world. Hopefully, any JavaScript browser-side programmer could intuitively guess what this program does. And then Node has this property where it exits automatically when there's nothing else to do. So if you put that into hello-world.js and you call it with the Node program, you'll get hello, and 2 seconds later you'll get world, and then the process exits. Okay, now a TCP server example. We'll start a TCP server on port 8000. We'll send whoever connects to it a message, and then we'll close the connection. So for this one, we use the net module, which we load on line 1. On line 3, we create the server object. And on line 4 and 5, which didn't fit onto the slide, you add a listener, very much like you add a listener for a click event on a button. Here you add a listener for a connection event. So every time somebody connects to the HTTP server, you get this callback. Oops. No. And then when you get the callback, you call c.end, which sends whatever this argument is to the client, and then closes the connection behind it. And then we listen on port 8000. File I/O, as I said, is non-blocking too, and this is usually hard to do, but we've got this thread pool built in, so we just use that. Here's an example of a program that outputs the last time EDC password was modified. So for this, we use the FS module, the file system module, and we pull out the function stat here. And again, we use the sys module and pull out puts. And we just call stat and then the file name, EDC password, and then we give it a callback. This sends the request to the thread pool and says, please make this stat call on this path over there, and let me know when it's done. And when it's done, it calls this callback. The first parameter is always an error argument, and the second parameter is the success thing. So usually this will be blank, empty. Yes?
Since you're throwing in the callback, no one's in a position to catch that throw.
Right. So there is a catch-all listener that you can add at some point. But right. So in this program, if there's an error, it will exit the process. The default action is to print a stack trace and then exit. But it is possible to do a catch-all sort of thing to log errors or whatever. Okay. So now just briefly, I want to tell you where I'm going with this program, or what I would like to do. So right now, people are using this very much as a little program to do real-time things, a little chat program alongside your traditional web stack, which you can't do because Apache sucks. Well, it doesn't suck. Apache's great, but it's not very good at doing real-time things because it creates these threads for each thing. This is kind of easy to script, and it does this real-time, you get this event mechanism into it, and so it's easy to add Node onto an existing website as just a separate process to do some sort of real-time behavior. And I think that that's what people are using it for right now. And so maybe it looks like this, which is where you have your front-end load balancer thing like Nginx, or I guess you guys use Apache here. And then you load balance across a bunch of Rails processes, because these Rails processes are very slow, and so you have to do this to achieve any sort of good response times. And then maybe you just throw in a node process on the side to do some little real-time application. But as web frameworks written on Node mature, I think it's not unreasonable to use it to build entire websites. The example, that benchmark that I gave you in the beginning, was loading a chunk of memory and pushing it to the socket very many times. We could just load our static files into memory and push them very quickly to the socket. I think there's a good case to be made why Node would be the foundation for a whole website. It needs some framework on top of that, right? You don't want to be writing all these system calls. You need something that gives you an ORM abstraction or something, right? It's too low level to be used for everyday normal web developer action. But even once we get to this point, you're probably still going to want it to set it behind some actual web server that doesn't crash or doesn't have exploits, just for security reasons. But load balancing won't be necessary. So maybe it's going to look like this. The node process is really good at handling requests, and you are not going to overrun it with requests. Maybe if you calculate primes or something like that, maybe then you'll need to load balance it across multiple processes. But if you're just shuffling data from the database back to the socket, I think one will very much satisfy your needs, one process, that is. And yeah, maybe someday when Node is stable and we feel comfortable using it, maybe our stack will just look like this. We can just write one script, spin up one process, and set it on port 80, and have it respond to clients. I don't at all feel comfortable doing that right now. Don't get me wrong. I would not do that with my own website. But I think that this is possible. So that's a lot fewer moving pieces than this setup, right? If you can just spin up one process and it has the power to completely saturate your bandwidth in terms of responding with HTML, then that's a pretty big simplification of the web stack. So yeah, any questions? Yes? Right. So your Node process has this main thread, which is JavaScript, and if you calculate primes or something, that's going to be run on one core. Inherently, it's a single process, and it will be restricted to that. Of course, you can always load balance, right? You can start a server file descriptor. You can fork the process n times, and in that way, you can achieve parallelization. Another way you can do it is write your prime calculation in C and use the thread pool underneath to spread out those things. It doesn't automatically parallelize your software, that's right. But it isn't inherently limited to one CPU in that you can always, at least in terms of server processes, you can fork your process, right? And it can be load balanced across machines or cores in the same way that we do right now. You have many web heads for a website, right? You can have many node heads for your website as well. Yes? So the question is, I guess I should repeat the questions. The question was why I don't feel comfortable running it as my main web server. There's lots of bugs. I spend my entire day fixing bugs. It's not stable. We'll get there, but not yet. It's going to crash, and there's probably exploits. You can probably go to /Ryan or whatever and get root on your machine. Nobody knows this, okay? It's not ready for that. There's a question back there.
So you saw, you had WebSockets on there on one of your slides. That's not built in Node yet, is it? WebSocket
No.
support. So for right now, we're still using a module to do WebSocket stuff. Is there a plan to move that into Core ever?
I'm kind of torn on that issue. I mean, WebSockets is hardly a fundamental protocol to the internet.
Right.
But it's so easy to implement that I kind of think that I'll just throw in the 10 lines of code and we'll have WebSockets. I'm not sure yet.
Okay.
Any other questions? Yes?
For a while, I saw a bunch of stuff about web workers. I'm not that familiar with it, but I didn't see it really mentioned here now.
Right. So my unit of parallelization is the process. And there's this idea of web workers that is coming out of HTML5, which is an API for creating different processes, not threads, but processes, because they don't share memory. I like this idea very much. I think the web workers API is great. And I was talking about before how you can fork a web server. I'm not going to actually give people fork because it's not on Windows, and like I don't want that concept. But you know what we can do is have a web worker and start a new web worker. And there's this idea of passing ports around. So you might create a server in one web worker and then pass it as a port into the other one, which is effectively the same thing as forking a pre-fork server, right? There's this thing with send message, the Unix call. You can send file descriptors to other processes and give the other processes the rights to accept connections on these other file descriptors. And so, right, in that way you can take a web server and start n processes, n workers, and pass the server file descriptor to each of them, and then load balance your web server across these n processes, but in the kernel, right? You just accept connections. Each of these event loops are accepting connections on these file descriptors, and the kernel is load balancing them out across them. Web workers is definitely on the table. I'm not. I think it's going to be like an API that's built in, but it's not there yet, and it won't be in the next release. So it's kind of getting pushed into the future a little bit. That, by the way, that stuff with passing file descriptors around. I had this architecture slide somewhere. Sorry. Right. The bindings for that are there. So you can create new processes and you can pass file descriptors around. The bindings for being able to do that are here. So it requires a bit of JavaScript, just a bit of JavaScript to write all this stuff. It's a bit of a painful JavaScript, right? These bindings are very low level. But that exists in Node today.
You made a lot of talk about the advantages of non-blocking over multi-threaded. Could you maybe speak about a few examples of when multi-threaded would be a better design choice?
Sure. I mean, there's a lot of trade-offs to do with the locality of your processing, right? So if you are calculating primes, it's definitely better to use threads to break up that computation over different things. But in terms of doing I/O, like actually accepting connections and pushing data around, I don't see any situation where threads are superior. Yes?
An example that I've encountered as that is in some sense the worst case programming style-wise for the pure event loop programming is you want to write, let's say, an interactive command line where you can type an expression in a programming language where the thing that parses the expression is a recursive descent parser. So the tricky thing about it is the recursive descent parser, if you write it in the normal call return recursive stacking way, then when it has partial input from the keyboard, it's not able to block and suspend the partial stack that represents the partial parse.
Yeah.
So how would you write?
Well, okay. Right. You're right, but let me think of something.
Good. That you've already exercised exactly the case I'm concerned about.
I think you have to do. Yeah, I'm not really sure how this is. It like this? So I've hit return there, and which it actually flushes it to the program, and now I'm doing this. So, but it's not very cool, right? I mean, it parses it, it gets an error, and then it says, okay, well, they're probably not done with it yet. I'm not sure. I think it's really not so smart.
So if it's when it gets an error,
you guys see this? I'm sorry. I guess I should make this bigger.
Yeah. So after you've typed the first line and you hit return,
sorry,
do you end up losing your parsing state so that every time you enter a new line until it's done, you have to start the parse from the beginning?
I believe so. Yeah.
Okay. Which I think, by the way, engineering-wise, is a fine answer. But in terms of costs programming style-wise, I think that this particular thing, I mean, it is the worst counter-argument that I've encountered in terms of effect on programming style.
Right. Yeah. Sure. For the HTTP parser, it does do these partial parsing, right? It can parse this far and keep the state and then continue that, but
how does it keep the state?
It just has some structure that it keeps.
Can you talk a little bit about handling binary data in JavaScript and your buffers and string encodings and such?
Right. So binary in JavaScript sucks really bad because internally we really only have strings, and they're essentially 16-bit arrays, which don't translate well into things that you can flush to the socket. In particular, in V8, it has this generational garbage collector where you have these objects in one place, and then suddenly V8 decides to move it over to some other place. And so V8 doesn't actually give you pointers to actual memory chunks that you can just flush to some socket. And so what ends up happening in Node very often is that writing strings, especially very long strings, is very slow because you have to copy it out of the V8 heap into some external heap, and then flush it to the buffer, to the socket. So what I've done is made this buffer object, which is pretty simple. It's just a mapping to some allocated memory that's outside the V8 heap, and you can load it up with data, and you can flush it to the socket very fast, which is what that first benchmark was. But that's not a really good solution because nobody wants to work with buffers, right? I mean, they want to work with strings. It's very natural. And so there's some work to be done in terms of being able to take a string inside of, you can pack arbitrary data into a string in JavaScript. That's not a problem, I think. At least it hasn't been a problem. The problem is really, I would love to have my data native storage in Node be a string and just fill it, just use the first 8 bits of all of these 16 bits and fill it with arbitrary binary data, and it won't be interpreted as UTF-8 encoded stuff. But I don't have the toolage from V8 to do that. So I have to use these external things. Strings have to be faster. Like being able to push this data to a socket has to be faster, and maybe that is going to require possibly like, giving V8 the responsibility. If they don't want to give me a pointer to the data inside their heap, then maybe I can give them the file descriptor and say, okay, you push that to there, which might be a nice compromise. I don't know. It's a hard problem.
So you spoke to the lack of infrastructure in terms of non-blocking libraries.
Right.
And I think an alternate approach that has been taken in Python, for instance, with Eventlet is they went and patched a bunch of libraries like URL lib2 and so on.
Right.
And you basically have synchronous looking code. You wrap it with some driver. You get a coroutine pool. You feed it in. It does magic, right? And it's like,
But it's magic, right? It's multiple execution stacks, and I think that's a difficult thing for just whoever, my girlfriend, to just come to it and understand. And I think that's an inherently more difficult concept to wrap your head around. That there's something different when you yield and go to a different execution stack.
But we're already trusting some kind of magical expert at some point. It can't be turtles all the way down. There's some C at the bottom of this that was written by an expert.
It's very simple, right?
It's very simple to you, and it's very simple to a lot of people. But by the same token, I think we're all just trusting somebody some way down. If we want to approach,
it's very much. I mean, not totally, but it's very much mapping directly to C. There's really not so much in between, which is why it's so fast. I mean, I'm not adding any magic here. Is the point?
Right, but that we're not solving the issue of not having the infrastructure to deal with it, right? Somebody's going to have to come and either write C bindings.
Oh yeah,
right?
Totally.
So
right,
I was just curious why.
Which is a problem, right? So you come to Node and you want to write your data, your program now, and you don't have a database binding, and well, okay, you're SOL. I mean, there's nothing you can do. You have to sit down and write some C code to do that, and that's just that's a result of being a very new project. Hopefully, if this project continues over the next year or so, those things will go away. And hopefully I've kind of infused the community with enough of this idea that everything needs to be non-blocking and everybody's thinking about it. And it says it on the website and it's all in the documentation that when somebody goes to write a binding to, MongoDB or whatever, that they sit down and they think about how to do it in a non-blocking way. Who knows? Maybe it turns out that 6 months down the line, a bunch of users come to it and they just start linking to whatever library, and then the whole thing falls apart. That could happen too. That would be dangerous. The project, the modules surrounding the project absolutely have to be non-blocking, and if they don't, then it doesn't work. Yes. Oh yeah, definitely. So there's a thread pool that you can use to run things on multiple CPUs if you want to. In general, the way I want to answer that is fork your process and use 2 processes and do IPC between them to distribute your computation. But if you, for example, there's different ways you can approach this. If you want to write, say, a gzip module, somebody wants to write that now, and we want to do it in a really cool way. We don't want to just link to libz or whatever. What we want to do is use the thread pool that's available to us. Start 5 threads, give it all a chunk of the data to compress, and then have them all return, and then you have your thing, your chunk of data deflated. So that would be a way to use the thread pool for these kind of small sort of problems. But for larger problems like distributing a website across multiple cores or whatever, you should definitely fork your process and load balance in some way, in some form or another. I guess that's not very satisfying to people, but I think that this is a really good way to distribute load across cores.
Are there any ways to actually talk to a database at this point with Node?
Yes.
Can you talk about that a little bit?
I believe there's bindings to, I wrote a Postgres one. There's a MySQL. There's a couple of MySQL ones. MySQL is hard because the actual like libMySQL client is blocking. But people are starting to figure out ways around that, which is actually understand the protocol that it speaks with the server. There's a Redis binding. There's a MongoDB binding. There's Couch binding. SQL. Oh, and at Joyent. Joyent's my employer, which, by the way, sponsors this entire development by employing me. Guess I should mention that. At Joyent, we wrote a really nice SQLite binding, which SQLite is the interface to it is blocking, but we actually do the calls in the thread pool and have them come back. So yes, there are ways to access the database. I'm not sure if I've listed them all, but probably. So not everything. Oracle, no. Well, okay. Well, because I imagine it as a node. I mean, it comes to this, how do you scale to multiple cores? You have a very fast single event loop, and you run that event loop on multiple processes. So it's one node of many. Obviously, you can't run Yahoo.com on one process, right? That's not going to work. For most people, it's going to work, but for Yahoo.com, it definitely needs to scale, and so Node is one node of a larger sort of system of things.